Hey, hello there, and welcome back for more Advent of Code. So today I want to revisit one last time the solution, if I can type something, the solution for day 23, the last puzzle that we did, which in the previous session we managed to get an answer for part 2 finally, but I'm not very satisfied with the solution. So mostly because it's a bit slow. So if we run this, timing it with the actual inputs, well, without recording, I think this takes like 6 seconds or something like that, but recording, well, it takes around 8 seconds, I guess, which is not too bad for kind of the complexity of this problem, I guess, but I would like to try to bring this time down as much as possible. Ideally, I would like to be able to run all of the solutions in less than 1 second, but I don't know if that will be possible or if I will be able to do that with this particular problem. But I have some ideas of some things I would like to try, so that's what we are going to do in this session. So okay, let's try to maybe take note of the things that I would like to do. By the way, if you haven't watched the previous sessions for this puzzle, and none of this will make sense, but well, that's how it is. So once again, the cat got into the desk and I have some cookies nearby, which I hope that she doesn't want to eat. Okay, so what we did for this puzzle was to separate the solution in two parts. First, we are building a graph given the grid, and we are building two different graphs, one for part 2 and one for part 1, and they differ in whether we obey these slopes in the grid or not. For part 1 we obey those slopes, and for part 2 we don't, basically. And well, the code for building this graph is quite messy, and I would like to revisit this, but that is not like related to performance, so we're gonna leave that for the rest. But let's say revisit build graph code, like try to clean it up. But it's not important for performance because this basically doesn't take time in comparison. Basically all of the time is spent here in find longest path for the part 2 graph, because basically this graph has a lot of connectivity and we are doing something pretty brute forcey here. So that's what takes most of the time that we see, those 8 seconds. So one idea that I have and I would like to try out is to change the representation of the graph. Instead of using a hash map from a 2D point to, well, a vector of points and their cost. So that's basically the representation of the graph. That means this point is connected to all of these points with this length, and like that would mean, for example, that the starting point is connected to this intersection point with the length of walking all of these tiles, and so on. But instead of using hash map and points, like we are not using that information about the 2D points on the grid. That doesn't matter once we build the graph. So this build graph thing could return a graph that just works with indices, like we would map each point to an index and then just have a vector of indices. So I think that could speed things up a little bit, because, well, it would be less hashing and like, well, mainly that, less hashing basically. So change graph to be a vec of indices instead of a hash map of points. Okay, and I think that's the first thing that we're going to try. And also related to that, one thing that I noticed on the previous session was that the size of this graph, so that is how many nodes there are, is not very big for part 1 or part 2. I think it was something like 30 something for part 2. We can see this graph size is gonna be graph length. If we print this, for part 1 is 26 and for part 2 is 35. So that gives me the idea that if each of these nodes would have a fixed index, we could, for example, identify in this algorithm here, we are storing entire paths that we are walking through, and the paths are basically vectors of points. And well, if we change the graph to just work with indices, this could be a vector of indices. But also, if we know that we have like 35 indices at most, we can, instead of having the path be a dynamically allocated vector, it can just be a number, a 64-bit number, and use it as a bit field, marking like with ones the path that you have been through, or the nodes that you have been through, and zeros the other nodes, and then checking. Like that would of course save a lot of memory. We wouldn't need to allocate new paths like this and pushing new nodes into those paths, so that would make that faster, but it would also speed up this linear search here, because we are asking if a path contains a node in order to, when we visit, in order to not get into loops, basically, and visit things in loops. We want to see if we want to only visit a new node if it's not contained in the path. And if this path can be like a bit mask, then this would just be a bitwise operation, and would be just like an O1 operation instead of a linear one. And that maybe will reduce the complexity of this algorithm. So that would be the second thing, which is kind of dependent on the first to implement, which would be use bitmasks instead of Vec paths, let's say, for finding the longest path. And finally, one extra thing that, like, if we do that, I would really like to see how that impacts in performance, hopefully positively. And if we have those bit masks, the last idea that I would like to try is to see if we can do some caching here. I'm not exactly sure how, but I'm imagining, like, here we are considering each of the nodes that is connected to the current node that we are working with here, and we are considering, well, that new path basically. But if you have already seen like that collection of nodes being visited with a given cost, like the maximum cost, and you're on basically on the same node or something like that, I would like to see if we have like some collisions of the same nodes with a different order maybe, but that would be exactly a bit mask or like a set of nodes. And if we have collisions like that, and we have already seen a higher cost for that, then it doesn't make sense to keep evaluating this, because we are interested only on the highest path. I don't know if that's made any sense to explain like that in the air, but it makes some sense in my head. So try out caching of node bitmasks, something like that. Okay, this would be what I would like to try out in this session and see what happens. So first things first, let's try to change the graph to be a vector instead of a graph. So how are we going to do that with this graph thing? In this build graph, we are, well, having a mutable variable for the graph and then in the end returning that. What we could do is to, before return, like leave everything the same, and before returning that, like convert it into a vector. But I don't know if that would be simpler than just creating the graph itself as the shape that we want. We would need some sort of mapping still, like we would need some sort of hash map for what are the indices that correspond to each point. But I think that would work. By the way, this is the grid. I think I would like to have type alias for this. So let's call this thing grids and have it be like the actual thing. So grid point graph. This takes a grid. Everything still works the same. And the graph, what we want it to be then would be a vector of vectors of the indices and their costs, basically. Okay, let's sketch that out and see what happens. So let's try to keep doing this for the graph. But okay, we already have like a problem here. We want to initialize the graph with a start, but the start is a point, of course, and an empty vector there. I think like could say something like we need an index for the start. Of course, the start will be index 0 on the graph. Like that's what makes most sense. So it would just be an empty vector, I guess, there. And I think we are going to have also like a hash map to map our nodes to their indices. So let's say node indices. It's going to be a hash map. I guess we can say from iter and just pass a tuple with a start, and the index 0 would be the start. Does that make any sense? Yeah, I think so. I think so. And we also know what the end is. So this thing get mute, and then we push how do we want to do this? Well, here we are already assuming that this, when it was a hash set, we were assuming that the vector was, well, the key was already there, and that would mean it would be the same as having an index for this thing, for this node, and then accessing that on the graph itself should also should already be initialized. and then we would just push this. I think that makes sense. And what would be the index for the end? That's interesting also. Maybe the end would be index max, the max value, or just index 1 instead of 0. That could also be. Yeah, I'm tempted to just say something like this. We'll start with 2 empty vectors in this graph, which corresponds to the start and end. Yeah, and here we are going to start with this start and end. The indices would be 0 and 1, respectively. Yeah. Let's roll with that. So here we would need to have the index for this node, node position. We are using that again, I think here, yeah. So we can probably convert this thing. Node position, previous node. Let's say node index, IDX for short, node indices for this node position, and we assume that this exists, and then here we're just going to say graph access by the node index push. And what do we want to push? We want to push the end, actually the end index and the amount of steps. So actually I would say something like end, let's have a constant or a variable for that. Does that make sense? Yeah, I think it does. Let's say let's have both for clarity's sake. Start and end index, and just have this here, starts index and all right, this makes sense in my head. Let's follow through. And here we are basically doing the same, but we are saying, hey, we reach xy. I wonder if we could generalize this, because it's kind of the same as this, but let's not overgeneralize yet. Like, we're not trying to make this code prettier, we're just trying to change what we do. Node index, what we do for generating the graph, right? So, well, instead of end index, we need to have give this thing a new index, like the xy, right? Yeah. So we know that this node, like here, basically this condition, this match is we are on a bifurcation. Basically, I probably could have written what these things mean. Like, this is a dead end, this is inside a corridor or whatever, like keep walking, and on an intersection. Okay. What is the index of this xy though? Maybe we don't have that. I suppose that we don't have it yet. Let's say this was node index. Let's intersection or new node index, node indices for this xy. I don't know if this is guaranteed to exist, but we will see it exploding if that's the case. But then we push new node index into here, which that will be the same as this line. Okay, and then this was a bit tricky. What we were doing was, hey, give me the entry for, like, we want to visit all the directions around this xy if it is an intersection, but only if we didn't know about this intersection. So the didn't know, what does that mean? I think the didn't know means basically we don't have it in our node indices, so or in the graph itself, like we don't have yet that. So I think we can do this. Like we can try to access the node indices, and if it exists, it's like, okay, we already know about this this node. We have that we already know about it means that we have already reached it in the past. So in that case, we don't do this for, and if we, but we still push this, the path from the node to this one. But if we did know about, if we didn't know about this, then we won't push. Sorry, I got a bit confused there for a bit. Or insert. We have the index. Yeah, let's try to sketch that out, what I just said. Node indices. We're going to try to get what's at xy. Yeah, so if it is some new node idx, I don't know if the name new makes a lot of sense, but if there was one, we already knew about it. We are just going to do this. I think we still need to do this. Or else, if it was none, then we need to create a new node index. Yes, and also do this and then do the iteration. So let's say let's new node index. In this case, we are going to create it. I'm sure that there is a better way of doing this with the entry API, like entry or insert with something and blah blah blah. But let's do it in a very naive way. What will be the new node index? Basically, the current length of the graph, I think. So graph length, like we are going to push something new into the graph. So I'm gonna do this and expand the graph. So push a new vector in here. And finally, we need to also put this into node indices. Insert at this xy, we're gonna have this new node index. Okay. And after this, after all of this, oh, we still need to do this, right? Beautiful. We are pushing here. Yeah, we could instead of pushing an empty vector, we can just push a vector with this, like save some of this thing, if it makes some sense. Here, I guess this is going to be a reference, so I guess dereference it or something. Here we are making what I think makes sense. New node. Wait, does it make sense? No, it doesn't. Wait. No, this is the new. These are the neighbors of the new node, and what we want to see is from the previous existing node we can reach the new node. Yeah. Okay, I was getting confused. This is a repeated line here, which I don't know how to unrepeat, but let's not worry about that. We are going to do also the loop in here. So for each neighbor position in the walkable neighbors, this is also kind of ugly, but let's not worry about that. We want to, unvisited, push this, and I wonder also if the unvisited could. No, okay, here we're still walking the grid, so we're still gonna work with points instead of indices. So okay, I think that should be kind of the same as before, hopefully. Node indices wants a type annotation, even though the Rust analyzer kind of knows what it is about. So let's have this thing be a hash map. And I think if I just say this, Rust is happy. Look at that. Is it better to write it like this or like intuiter collect? No, definitely the previous. I would like to not have to put the type annotation though in here. Like it is a bit ugly. I don't know if this is valid syntax. I think not. Okay, that is fine. Hopefully the graph is still the same as before. Maybe we could have printed the previous graphs and the new ones to see if they make any sense, but well, too late for that. We'll see how it works. Here we are getting the graph, and interestingly, start and end are no longer gonna be needed because, well, they actually should be indices. So, well, let's bite the bullet and pass the indices here. It's kind of unnecessary because we already know that start is 0 and end is 0. So, yeah, let's actually, I would like to do that. Let's put this, promote this to a constant and promote this to a constant. Move the constants out. We use the constants here. We set them here, and we don't need to pass them around in here. So now start is going to be, let's work with indices and see if everything makes sense. So the paths, yeah, are going to be vectors of indices. Nodes are indices also. So here we are, if the last node is the end index. And here, I guess this is a usize, so accessing this should just be this, and node and cost are the correct type, so everything is happy about that. Great. And we don't need to pass the start and end here. That's great. That's great. And does this work? I wonder. Oh, did we get the correct answer? I don't think that this is the correct answer, right? No, it is. Okay. We did get the same answers. And it runs significantly faster. Look at that, almost 8 seconds before, and well, 6. It's not double faster or anything, but it is quite faster. A couple of seconds faster than before. And surely if I wouldn't be recording, this would be quite faster, but that was nice. Trying it again to have less noise maybe. Okay, yeah, around 5.5 seconds seems to be the time. Great, and that wasn't that bad of a refactor, I think. Yeah. That makes some sense to me. It's a bit more bookkeeping here in this grid walking code, but I think the result is worth it, not only in performance, but also like the graph is simpler than we have before. And now this code just works with a graph that does not concern about points or like grids or anything about the grid. And actually now, like the start and end, it doesn't make sense to pass them to build the graph. We can have those inside, I think, inside of here. So height, width, start and end. We don't pass these things here. We don't pass them over here. And yeah, we don't also need the type for point. That's also nice. Start and end here are kind of like the positions, which I wonder if node indices start end. Like if the graph is just about like indices, we could call these indices like the actual nodes, I think. I think it would make more sense to say, okay, these are start and end nodes, and don't call them indices. And these are basically start and end positions instead of these things. So I think the end is also only used for here, for this. So yeah, let's maybe make that little refactor. Let's call this thing just simply start and end. And these are gonna be start pos and end position. Okay, kind of superfluous thing, but like, let's make this thing, only the build graph cares about positions, and after that it's all like nodes and indices. So we have the graph, great. Do these names still make sense? Yeah, these are positions, so it does make sense. Node position, node index, yeah, it does make some sense. It's the end, yeah. This is surely also still like, we can clean it up, but that is not what we are doing now. Now we are doing just this. I'm just looking to see if there is more like graph jargon that or like things that became bad variable names with this refactor, but I don't know, I cannot see anything. And then find the longest path. This doesn't talk about positions or things like that. The path themselves, well, this stack, let's call it like, these are the things to visit, let's say. So maybe a bit of a better name instead of just calling it stack. We have paths and path cost, last node. Sure. Instead of saying last like this, can't we, oops. I mean, between that and path length -1, I think I kind of prefer this, although it's kind of the same. Yeah, this looks alright. Does it still run? Does it still give us the same answer? It does. And if we run check the samples, yeah, it also passed for day 23. So okay, that was a nice refactor and also a nice improvement. Oh, by the way, I think now that we have simplified this thing, we can even go ahead and like inline these things and not have like graph part 1 and graph part 2. It's just, yeah, look at that, much better. Yeah, now it looks quite nicer. All right, now we can commit this, just this thing, commit and say day 23. Use a vector for the graph representation vector instead of a hash map. A vector is a hash map for the graph representation. This improves or reduces the runtime from around, let's say, around 7.5. Sorry, today I'm typing even worse than I'm used to around 5.5 seconds, and also makes the graphs simpler. Okay. All right, that was the first thing that I wanted to do, and it's done. Now, for the second thing, yeah, trying out the bitmasks here instead of saving all the path. That would make sense, but it's not just about saving the bitmasks. Because we also need to know, well, what is the last node, and if you just put the bitmask there, you don't know which bit is the one. So we are going to have basically, let's say, a bitmask, and let's say also last node, or simply let's just simply call it, well, let's call it last node for now, just to have the same variable names as before, but then we can change it to just say node bitmask and path cost. Yeah, and the path cost, yes. Okay, and the start, how are we going to do this? Okay, we're not going to have vectors here. The path cost is going to be 0, yes. The node is going to be the start node, which is also 0. And the bitmask should be, I think, well, is 1. That means the bit corresponding to this node is present. Maybe a bit obfuscated to write it like this, but let's roll with it. This should still be the same, and yeah. And here we are going to, yeah. Here's what's, we don't have the path, okay? And we do have the node, which is like, how do we ask if the node is in the bitmask? Well, that is the same as saying node is basically a number. So we're gonna say bitmask. We AND it with a 1 shifted by the node number, like the index. So if it is 0, the start is shifted by 1, or it's not shifted, so it's still 1. If it's 1, it's shifted by 1, it becomes 2, and so on. The precedence of this, I think, is correct. And if this is non-zero, it means that it is there on the path, the bitmask thing. Like maybe the name of bitmask could be a bit better, like visited nodes bitmask or something like that, but we know what it means. So yeah, if it is, then if the result of this is non-zero, it means we already know about that. So we want to filter the ones that we don't know about. So the ones where all of this thing is 0, I think. And now, instead of saying new path, we're going to have a new bitmask, which we can compute directly. It's going to be the bitmask. And this is also another like linear thing that we are saving, like the copying of the paths. Bitmask, or this same thing, like 1 shifted by this, and the precedence, I think it is correct, yeah. This is gonna be the new bitmask, and yeah, I think that sort of makes sense. So we are going to then push to visit this node for this new bitmask and for this sort of new cost. And maybe we can be a bit obfuscated and inline everything. Maybe not. Okay. Awesome. Awesome. So does this work? Is this everything that I need to do? If we run release mode for the actual inputs, wow, it runs super fast, but it didn't give us the correct answer. So this is not correct, but it is the correct answer for part 1, surprisingly, and not the correct answer for part 2, which is a bit surprising. But it also went like super fast. I was not expecting that kind of speed up, but we are not doing so. Let's not get our hopes up, because definitely made some mistake here. Where though? Like, we are initializing this correctly, I think. Start, the bitmask only has this thing turns on, which is the starting node, because it's 0, fine. Here we are filtering out, yeah, the ones that are not in the bitmask. And then we OR that bitmask that we have with the node. I'm a bit paranoid about precedence here, so let's add some extra parentheses. This is surely not. I want to also check the samples to see. Yeah, it also works with the sample. It also works with a sample. What a weird thing. Actually, like, it's stash. Did we have the correct answer before, or am I tripping? Yeah, this is the correct answer. Okay. So it is a stupid mistake that we introduced in this relatively simple change here. Well, it's not so simple, but starts like it's a node and it's of type usize. Oh, look at that. Thanks, Rust Analyzer. Bitmask is 32 bits integer. That was stupid. I'm really interested on this being 64 bits. So U64 is very important here. So if we run with this, yeah, look at that. That speed up was amazing. Okay, it's not as fast as this. I don't know how much it was, 30 milliseconds, but it's, well, 300 milliseconds is like a third of a second, and we are getting the correct answers. This was a much bigger speed up than I thought it would be. So just using a bitmask, which kind of makes sense, you know, you're changing a linear structure with just a number, but it is pretty amazing. Awesome. And actually, I would like to do a check here to see, it's kind of an assert. Maybe we can say ensure. Anyhow, ensure. What we want to ensure is that the graph length is less than or equal to 64. And look at that ugly symbol. It makes me realize that I don't have the ligatures enabled, which I have disabled and enabled for previous for some previous problem, but look at that, now it looks better. So let's say graph is too big for bitmask size. All right, and this would require us to this thing to be a result. No problem. Let's make it a result. It's fine. I would like to have this kind of guarantees. So here, since this is a result, we have to propagate any error up, and in the end we're just going to say okie dokie for the max cost. By the way, this thing will return the bad answer of 0 if there isn't not a path to the end, but I don't really care, I think. Or do I? I don't know. Maybe I care, but what I really care about is this performance improvement. It's so nice. So yeah, let's now also maybe put better names to these things. This is not just the last node, it's the current node. So let's call this thing just node. And inside of here, well, wait, we weren't using, yeah, we're not using last node inside of here, so there's no collision to doing that. But let's not call it like this, just node. Let's call it, well, it's new node or neighbor node or something, but new node is fine. Yeah, new node. Node cost is maybe new node cost, or I don't know, something. Whatever, new node. We are going to filter. Yeah, this makes some sense. I'm not sure if this filter is like, maybe an if here makes more sense to me. If we already know about this, means basically means this. Like if we already know about this, or sorry, if we don't know about this, then we're gonna do this. We can remove the filter. Yeah, I think that this is better. And this is not the node, this is a stupid mistake. Yeah, I think I do prefer to have like the if inside of here instead of the filter in this iterator. A bit more imperative, but it's fine. New bitmask. Yeah. That cost, new cost. I'm not sure about the names of this node bitmask. Actually, like last node was not that bad of a name. Yeah, because this represents like the last node in the path that we are taking. So let's call it that and go back to the previous naming. This still works, right? No. I broke something. Surely a stupid mistake. Do I actually want to? No, I want to ask the same thing as before, if this is equal to 0. Yeah, okay. Great. Yeah, and also we have the bitmask, like accessing the bitmask a bit close to each other, so it makes a bit more sense, I think, the kind of operations that we are doing there, so that's nice. Node, new bitmask, yeah. And this bitmask is actually like, I would call it path bitmask as well as path cost to like, yeah, to represent what we are doing here. And new bitmask is alright for this name. So yeah, and then we have this to visit. Great. We can call also this thing new cost. Why not? Yeah. Node. We're going to visit this node with this new bitmask and this new cost. Yeah. Makes a lot of sense to me. Now we can finally run check all and not have it take an enormous amount of time. It's just I don't know, 1 or 2 seconds, which is fine. So yeah, this was a much better refactor than I thought it would be. I expected to have some speed up for this, but not just what was this, like we went from 5.5 seconds to a third of a second. That's a lot. That is like 5 this amount of milliseconds, and if we time it, we are in 320, let's say, I don't know, 320. So this was a 17x performance increase or something like that. A lot, yeah, it's just a lot. So that's really, really nice. I'm super glad to have done this refactor. So let's commit it. Day 23. Improve performance by using a bitmask instead of a Vecs path. Yeah, something like that. It makes sense in my head at least. So okay, this is awesome. Oh, by the way, something that I was considering is like, do I want to like float up the case of not having a path? Like if we start this max cost as none, and then at the end we can say, okay, hey, if give it a context, you know, this is context is a method of anyhow, which is kind of like the okay or on options, and say, okay, no path found from start. No path found. That would be enough as a context, and that already returns a result. So that's kind of nice. And then here we want to, what do we want to do? Basically want to, if it exists, put the maximum, and if it doesn't, well, we know that it exists now, so we can say, hey, this is sum of like the path cost, the maximum between that and something like this. Is not very pretty. It's not very pretty. If I turn it the other way around, it still won't be too pretty. If I say max cost and wrap or 0, and then max of that and the path cost, I mean, it would still work, but as long as this doesn't affect the runtime, and it actually kind of does. Or maybe it was just noise, but it kind of looks like it's a bit slower. Yeah, no, it's just noise, or I don't know, the numbers when not having that seem a bit lower, so you know what, I don't care of giving a bad answer if the paths are not connected. Like, I'm not so worried about correctness of the results, I'm just more worried about like performance, of course. That's why we are optimizing this, and also like robustness, like not having the thing panic with bad inputs, you know, checking preconditions like this and things of the like. But if we don't have, like if we don't give the correct answer, I don't care so much. Like, it's just a puzzle, man. All right, so, oh, did I commit the README? That was a mistake. So, did I commit the README here? One file change? No, did I commit it here? Where did I? Oh no, I stashed this thing. So we can unstash it, and we have the README back, and we can get rid of this optional thingy. And okay, back to the README. We have done this use of bitmasks, so that was really nice. Now I think that maybe caching of these bitmasks doesn't really make a lot of sense, because this is already much faster than I thought that I would get to by doing this optimization. But I'm curious to see if we have some collisions. So how do we ask that? Maybe let's make an experiment. Let's say let mute known bit masks and just have a hash set. I don't care about the logic for this now. We could have this at the beginning, but I don't care either. So when we are evaluating a new bit mask, we want to see if we already know about that bit mask, and if we already do, and the cost, well, let's only print like if known bit masks contains can I ask this? Do you contain the new bit mask? Then I don't know, print bit mask already known. I think this should happen. Otherwise, well, not otherwise, but in any case, we are going to insert. I don't know why this Rust analyzer is not working. Maybe I didn't do the imports. Great, import the thing. Sure. So okay, does this happen? Run it with maybe with a sample. Okay, yeah, the bit masks are known. How many of them though? Let's call this thing hit count. Instead of printing this, let's do a hit count +1, and then print line known bit mask hits. It's going to be the hit count. How many times does this happen on the inputs? Well, it happens 70 times for part 1, it seems, which is it's not too many. And it made the thing take a lot of time because of all the hashing. So I'm already suspecting that this optimization won't be worth it because, well, but the number of hits on part 2 is also 25 million. So I don't know if it will be worth it or not. But hashing is expensive, as you can see. Okay. Maybe using Rust C-hash, which were we using that on Cargo TOML? No, we don't have Rust C-hash as a dependency yet, but we can try it. If hashing is expensive, well, we already know it is, like hashing everything is expensive, but we need to then implement the logic. What are we going to do? Actually, this won't be. Let's try to do this caching and see. It won't be a hash set. It should be a hash map, where what are we going to do? Hit count. We don't care about that. We are going to say get the thing for this new bitmask. So if let's some known cost be this, and we are going to put bitmask under cost, and if the known cost is greater than this cost, like the new cost, so let's put it up, this new cost, if it's greater, then we continue on, right? We continue with this, like we don't do this to visit push if it's already a known cost, and because we know already about visiting all of these nodes, but I don't know if this will be exactly correct. Let's do continue here, and otherwise we are going to insert the new bitmask and new cost, and this is, yeah, sure. I don't know if this logic is correct. Well, almost, like, what was the answer? It's not exactly that, but it's surprisingly close. Again, it was right for part one, which I guess makes sense because on part one you don't do much of like backtracking or anything, but for part two it's a bit shorter, which I think I know why, because yeah, the known bitmasks we also need to know like which node we are in, so it's not just the bitmask, like, because it can be the same bitmask as a previously walked path, but we are not going to be standing on the same node. I don't know if that makes any sense, but what I mean is I want to know about this bitmask and these nodes that we are considering here. Okay, and then we are going to push like the keys. It's going to be the bitmask itself and the node. So with this is the logic right now? Like, do we get the correct answer? Why is it taking so freaking long? Yeah, right, this is the correct answer, it seems. Yeah, it is. But it is freakishly slower. And actually, does this happen? Like, we knew that we had hits before, but I don't know if they were, because we were only checking for the bitmasks, but not which nodes we were standing in. So let's just print hit. hit. Okay, we're having hits. We are having hits of this. So we are saving some things to visit, like we are saving some pathfinding, but it's not worth, like the amount of hashing is really not worth it. It's not worth it, man. We could change this with or insert or something like that to have the known bitmasks. Like with an entry API, we can avoid hashing this twice. But let's actually try. Like, I don't think that this optimization will be good enough. But let's actually try using how is it called? Rust-C hash with that. So we should have Rust-C hash, and this hash map. Let's import it from no. Wait. What I want is use Rust-C hash, fx hash map, but let's call it as hash map. And what's your problem here? Unnecessary braces. Okay, yeah. Didn't know about the syntax. And then you don't like new here because I know that you like to be called default. Okay. Does this, like, how? I don't remember how much time it was taking before. And now it's compiling Rust-C or something. Rust-C hash. Doesn't look much faster. In fact, it's slower than the standard hash map. That is surprising, right? That is quite surprising, actually. I did not expect that. Yeah, import the, and again we have to make this dance of changing default with new because reasons. If we run it with a standard library hash map, is this one of those cases? Yeah, it looks like the standard library hash map is faster than Rust-C hash for this case. I don't know why, but that's okay. Like the things here are like two 64-bit numbers, so it's not like difficult to hash or anything, an expensive hash or anything, but yeah, it's not worth it, this thing of caching the results. Which, okay, it's a pity, but it was a worthy experiment, I think. The logic is correct, right? Like, we are skipping some cases. We know that we have hits here. We are skipping some cases, and we're still having the same result. So logic is alright, but this is a good lesson of sometimes hashing. Like sometimes an optimization that looks like an optimization, like a cache, might not be worth it if the cost of accessing that cache, is too high. Like for instance, in this case, doing the hashing, it turned out to be more like higher cost than just computing the thing. So try out caching of node bitmasks. Yet we have tried it out and it's not worth it. If we run it now, we should have 300 milliseconds runtime, which is much nicer. And then let's revisit the build graph. This find longest path, I'm very pleased with this code. It turned out to be quite nice. And I really liked the bitmask refactor. Then we have these type definitions, we have this start and end constants. Maybe let's give it a little bit of space because these are two different things. Start and end position is fine to have it here. Sure. Node indices and the graph initialization is not very pretty, but it's fine. Type here is ugly. Can I give it a type like in here? I don't know where the turbofish. Yeah, maybe that's a bit of a less repetition of HashMap. Still, this long turbofish is not the prettiest, but okay. Sure. And this graph probably is not needed here. Can probably be inferred from being the return value. So, okay. Then inside of here, I'm pretty sure that there's a lot of things that we can improve. We are grabbing the node index, so we know that this node that we are visiting now should already have an index. Like we already know about this node because we are doing that here. Can this be changed though? Could we change this to just push the node to be processed and then do the initialization of that node? I don't think so, because we need to know the index to know that we are reaching from this index to the current node index to the new node index. So we need to do this here. This repetition here, I don't think that we can get rid of, or I'm not sure how to. Gets or like if we did that gets or inserts. I think we might actually. Yeah. Okay. I think we can do like refactor these into one of those entry how do you call it, like HashMap entry API. So we would say like node indices, give me the entry for this X and Y key, then or insert with, we're gonna pass in so this is okay, the entry did not exist. What are we going to do in that case? Then it's basically this code, I think, but not all of it. So we're going to create a new node index to be like, that's what we are going to insert. So this is what we are going to return in this thing. We are going to also push it into the graph, so we know about that index. Sure. Yeah. We can then, this is what I think is going to be moved outside. Or is it? Wait. No, this insert is what the or insert with is going to do. Like it's going to insert a new index in the known indices, and then the update of the graph, we can do it afterwards by saying, because this or insert with is going to return a reference to this new node index, I think. So let's new node index is going to be this, and we can even dereference this. So I think that should be what we wrote here, should be the same, should work the same as this. I'm not really sure. We are just going to check this by running the actual input, and it ran and it gave us the correct answer. For some reason, I'm now suspecting like how much noise is there in these numbers. This shouldn't be changing this, because building the graph should not be faster this way or slower. But it kind of, no. There's a lot of noise. There's a lot of noise. For some reason, I am a bit paranoid. I don't know, it kind of looks, I should be timing these things, but I don't even know if this refactor is actually, like if it makes things more readable at all. So we changed some things over here, but this thing is like, let's see it from a vantage point. What I do like is, like, we are considering, okay, if we don't know about this node yet, we make a new name for it, and yeah, I think I do prefer the new version, even though it's, I don't know, questionable how much of an improvement it is. We can even like get rid of this and just say graph length -1 here. Should just work. So if we don't know about this, we're going to do this for and push things to visit. Then we are going to increase the graph and say, okay, it was the previous length. Sure, and then we use that thing. I think this should still, everything should still work. Yes, you can even check all the things. Okay, yeah, that's fine. I'm fine with this. What I'm not fine is with all the gunk here. Like all of this stuff is not very readable. Okay, reaching the end, this is fine. These are the walkable neighbors. Yeah. We are mapping into this thing. We are doing this. Can't we actually, yeah, look at that. This I think can be refactored into, like, instead of saying, okay, match the tile, and if this is the condition, then return none. If this condition, return none. If this condition, return none. We could actually also say, yeah, return none in all of those cases, and otherwise return this sum thing, and actually like return result of this, and we can also get rid of these return keywords. That should still be the same, and it is great. And also I think we can, since this is like this is mapping to an option of a point, we can use, instead of doing and then here for this optional tile thing, we can early return here with this operator, which should make things much better, I think. Get, and just simply, yeah, take out the return, else return none or whatever, and just say, hey, let the tile be this thing, and we early return. That's also possible. The tile is a character reference, but for some reason it doesn't need to be dereferenced here, so okay. But okay, this is now quite a bit shorter. We can maybe even make it even shorter by inlining that. Not much better. It's not much better. Let's keep it like this. Fine. All of these so far are good changes. This though is quite ugly. Walkable non-previous neighbor. So we want to know about this and the walkable neighbors because we have can we just get the count of this? Like do filter and then count and use that here? No, because then we would need to use when we keep walking into that. But actually this doesn't need to be a static array. I think I meant to use an iterator here. And by the way, isn't this map? If we make this thing an iterator, and we, instead of saying map, we filter out the previous position. So we ask if the neighbor is some and is the previous position. Something like that. Even I don't know if option has a, does it have a contains? It would be really nice if it had a contains. Oh, I didn't have a browser yet. Rust option contains. Surprised that. Yeah, you can say if let some, but it's kind of saying same as this. Okay. So if this is an iterator now, we can just ask count of this, and here previous non-walkable neighbors, just say next and then wrap. Although if we have done counts, we will have This is an iterator of optional things. Not great. Is some and. We actually kind of want to filter map this, I think. Which would, how would we do that? We can't we do something cheeky like this? Almost, but not quite, I think, because if we can early return maybe, then like this, try. But if we say, okay, if it was the previous position, I mean, the filter that we were doing before was working working correctly, and then is some and we can actually flatten this, right? Flatten, and then the neighbor here is going to be a reference, so we can just filter the one that are different to the previous position. That is actually what we wanted to say. And here I guess we can dereference a couple of times. So now this should be an iterator of actual positions. So now this should be a position which we can dereference here, and this should have been moved, right? Immutable variable. Yeah, what I think I want is like to clone this iterator and borrow after move. Of course, we have to do a couple of clones. I don't know if that's still working as before. It seems to yeah, okay, it still works as before. I don't know if it's better than what we were doing before though. Maybe it's not. But we converted that like static array to an iterator. We are just it's a bit ugly. That's kind of I kind of just want to count, but no, it's not just count. I also want the value of it. Can't I like pattern match this somehow? I get the iterator. I think I might be able to, and that shouldn't like impact performance that much. Non-previous neighbors. If we collect this actually, if we collect into a vec and then do something like, hey, match, can I match like this guy to this, and say here nx and y in a really cool way. I think in order to do this I need to take a slice of this. Okay. Cool. So okay, if we have only one, we're going to do this. We maybe don't need this. And these are references. We can maybe dereference here. Does this work? Because this does look a bit better than before. Yeah, it looks like it. And if we time the thing on the input, I don't think that this should be... Yeah, it's not slower, even though we are allocating something, because this is not the hot path. It's not the thing that worries me. Although we are doing this inside the loop that we are walking, so it's interesting that these allocations really don't matter. Nice lesson also. So okay, here we have like a single vector. Yeah. This is quite nice. And the walkable neighbors, we still need them because we cannot just extract here the positions and only push that. Although I never tried that. Like, I don't know if it's any other case, like neighbors, and we just use these neighbors here. Neighbor position, it's double reference, double D reference here. Like, does this work, for instance? I don't know. No, actually, again, we get good answer for the part 1, but not for part 2. So it is important to walk around all the walkable neighbors here. So basically this is 0 and only one case. We can just, instead of doing this, we can just say this is a neighbor position. Yeah. Yeah, this is nice. And what else did I want to do? I think this, even though it's a bit more, I don't know, some things became a bit more verbose, like this iteration here. It's not worse, I think, than it was before. That's not really a lot to say, but yeah. By the way, if this was like having this vector collected here was not that bad, I wonder if when we are excluding the previous, like if we can just allocate the vector here and not have this thing be an array of optional things, just have the walkable neighbors directly. Maybe that also would simplify some things up, although this is not very complicated and we're just flattening this here, so yeah, it's not that bad. Yeah, okay, let's say that this is not so horrible, although I don't believe it that much. Walkable non-previous neighbors. Yeah. It's a bit of a mouthful, but it is explicit at least. So let's leave it like that. And yeah, overall, I think this is not too pretty of a code, but it's not that bad either. Let's look at the changes we did, if they make things better or not. This is just nitpicking. This is kind of nicer, I think, than what we had before. It's a bit shorter. It's nice. This is not shorter than what we had before, but I would say it's a bit simpler because we are not doing this iter flatten here. We are just matching, yeah, we're matching this thing. And especially this, like the case of keep walking became a bit simpler. We're not extracting this thing like this before. And yeah, I think it's not that great of a, like too much of a nice refactor this, but for the build graph. But the other things like the performance improvements were great. We are now running this in like 300 milliseconds with some variable timing there, but it's running much faster than before. So that was the main objective of this session. So, oh, damn it, my cat was attacking the cookies. Simona, ¿qué haces, Simona? Come on, time to go out. So I think there is a cookie that has been licked by the cat. I will put it on the side to give it to her, but the rest of the cookies I will eat myself. All right, what I wanted to say here, day 23, slightly or improve builds graph code slightly. Can I type maybe? What am I typing? Right. All right. Yeah, that's what I wanted to say, and that will be it for this video, I think. Does it make sense to have some thumbnail for this? Maybe it does. I don't know. I never know. But it's always nice to see colorful letters on the terminal. So let's do that. Let's do a toilets call. Event of code day 23. Longest path search. Let's say longest path refactors. Or no, this is actually like performance improvement. Yeah, we increased, like we made performance much better. So perf improvements, say speed up from let's say 7.5 seconds to 300 milliseconds. I don't know if I need to escape this exclamation mark here. Ooh, look at that. It barely fits into the terminal, but it looks pretty nice. Yeah, speed up from 7.5 seconds to 300 milliseconds. And this is actually not like lying or anything. It's actually what happened. So it was actually a very nice performance improvement. And the best part of the code, I think, is definitely this find longest path function that's quite short, and it's actually doing a lot of work, and it's doing, yeah, the bitmask trick was really nice to implement. So yeah, that will be it for this video. I'm very glad to having this bitmask idea work so nice. I actually wasn't expecting to get such a nice improvement. So yeah, that will be it for this video. As I've said like 100 times already, but as usual, if you have been watching, thanks for doing so, and see you later. Bye bye.